The ballistic pendulum is a practical way in which we can observe inelastic collisions. And so we see here a situation where a projectile is fired into a wooden block. So here, this could be our musket ball. I'm going to label our musket ball as mass 1. And this is our wooden block. It's suspended by this string here. We'll call this mass 2. You can see that the wooden, or I'm sorry, the projectile is moving at a very high velocity, and so we can see that this has a really large, relatively large momentum. Where over here you can see that there is no momentum at all because the wooden block is stationary, it's not moving. So the momentum of this block is actually 0. Let's go ahead and break this down. So this is momentum of object 1 and is the momentum of object 2, both of which can be broken down as mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial. We can see here that because the block is stationary, the velocity is 0, which in turn removes this part of the equation, because since the velocity is multiplied by the object's mass, because there's a multiplication factor and that the velocity is 0, this whole part is 0. So we can just remove that part of the equation. Now, following collision, so let me just write this. This is before this situation right here was before the collision took place. Now, following collision, you'll notice that the pendulum, I'm sorry, the suspended wooden block, I should say, gets struck by the projectile, which is this musket ball. The musket ball fires and it strikes the suspended wooden block and embeds himself within the wooden block. So we do see that the block gets deformed as the projectile impacts it and embeds himself within it. This is a prime example of inelastic collision at work. So we can see now that the two masses are together, which we can actually signify like this in a equation, where we can say the mass 1, which is the projectile, embeds himself with the mass of the wooden block. So both masses are together. So following the collision, the projectile becomes embedded in the block, and we do see that some of the kinetic energy gets transformed into thermal energy and sound, because we definitely hear that we can definitely hear the collision, and some of that collision has been some of that energy has been given off as heat and sound, whereas the rest of that kinetic energy has been given off as the motion of the wooden block as it now behaves as a pendulum. So we can see that the wooden block is now oscillating back and forth like a pendulum. And both the wooden block and the projectile, the musket ball that impacted it and embedded himself within it, both of them are moving at as one velocity, which we'll label as velocity final. And so what we see here is a prime example of an inelastic collision. And this is the equation we would be using if we needed to solve for it mathematically. Now, say that the question is asking for the initial speed of the projectile. So we're looking at the velocity at which the projectile is flying before it impacted the suspended wooden block. How can we solve that? Well, first of all, remember that the initial velocity of the projectile is signified as velocity 1 initial. So that's actually right here. We're trying to solve for that. let's say that we know the masses for both the projectile and the wooden block, okay, but we don't know anything about the speed at which the projectile with the wooden block is going as soon as the collision happens, and now they're moving as one unit. So as in other words, as the projectile embeds himself within the wooden block, and now the wooden block with the embedded projectile, with the embedded projectile swings back and forth. We don't know anything about the question. Did not specifically state anything about how fast it's going, so we don't know anything about this. Again, we do know about both masses, so we know mass 1 and mass 2. We're trying to look for the initial speed of the projectile before it struck the suspended wooden block. But we don't know anything about the final velocity at which the embedded projectile with the wooden block is swinging as it oscillates back and forth like a pendulum. So how can we solve for this in order to solve for the velocity at which the projectile was going initially? Well, when we're dealing with ballistic pendulums, there is another important concept that is going on here. The first concept is that momentum is conserved. And so, we can see that the collective momentum before the collision equals the collective momentum after the collision. We understand that. But another thing we need to understand is that conservation of energy is also in play here. And if you remember your definitions for conservation of energy, we can say, give me one second, let me just rewrite this. So conservation of energy, we can say that the total mechanical energy that we have down here as the projectile with the pendulum is moving, the collective mechanical energy that we have down here eventually equals the collective mechanical energy that we get when the pendulum is now at this point, where we can say that it's swinging right here, just like that. So here's the wooden block with the embedded projectile here, and at this point you notice that it is at a certain height from its original position. We can actually use the concept of conservation of energy to ultimately solve for how fast the projectile, the embedded projectile, and the wooden block is moving just as the collision has occurred. Right after impact, how fast is it moving? That's what this VF represents right here. If they didn't specifically give us the velocity final, we can still solve for it as long as we know the height at which the pendulum reaches before it stops, changes direction, and swings back the other way. And so the conservation of energy states that the kinetic energy, you notice that down here, this whole thing is all in motion. The kinetic energy is equal to the potential energy that it stores as it reaches the highest point, because you notice as it reaches the highest point, the projectile with the, or I should say the pendulum with the embedded projectile eventually slows down and stops at that highest point, then changes direction in a moment's notice and swings back the other way. So at the point where it stops, it basically has stored up all of that mechanical energy in the form of potential energy. And so we can say the kinetic energy that it has at this point equals the potential energy that it stores up at that point. And so, the equation can actually be written as kinetic energy equals potential energy. Now you understand that both of these has equations of their own. Kinetic energy, if you can recall, is equivalent to the object's mass times velocity squared over 2. where the potential energy due to the object's gravitational acceleration and height could be written as mass times gravity times height. Once you have the equation written out as like this, you'll notice that the masses will cancel out, and now the equation has simplified to this: velocity squared divided by 2 equals gravity times height. And notice that that velocity represents this final velocity, the velocity at which the pendulum and the embedded musket ball, the projectile, is moving. That's what this velocity is all about. We can solve for that by just taking the 2 and multiplying it on both sides like this. And so the equation can be rewritten as velocity squared equals 2 times gravity times height, which in this case, you notice that you got to take the square root. So the equation can now be revised to velocity equals the square root of 2 times gravity times height. So knowing this, you can use the conservation of energy to ultimately find out the velocity at which the embedded projectile with the wooden block is moving at this point. And then once you find that, you can eventually find out our initial velocity at which the projectile is moving right before it strikes the pendulum.